But I'll introduce myself again. So my name's Ian McGovern. You can call me Ian if you'd like. You can also call me Craig, which is the name of my twin brother, if you want to antagonize me. That's okay. You can call me Twin. That's what my brothers call me typically because they can't tell which ones of who we are. So growing up, I always heard like, Twin, get off the couch. And I was like, bro, I live with you. Come on, bro. Anyway, my name's Ian. I don't know if he's posted my email. I should ask him to post my email on the website. This is my email, in case you're wondering. McGee@gmail.com. Not sure if this is anywhere. Feel free to email me. What I've been trying to tell people is that I'm teaching two 100C classes right now. So I'm teaching this class. I'm also teaching it for Zhang, Mike. So please, if you email me, just put a meanie somewhere in there. Because it's really confusing when people are like, oh, I have a question on homework on question 3 of the homework. And I'm like, I don't know which question 3 that is. So and then I also sent out a thing, but my office hours are Tuesday, Thursdays from 12 to 1, and it's a different Zoom link that I sent you. Okay. So how's everyone's day going? Is it going well? What's up?
Good.
Good? That's
Yeah.
nice. I had a nice day. You're tired?
Yeah. I got
I
like the
am.
vaccine yesterday.
Oh, you
So
did? How does that go?
yeah,
Which one
so I'm
did
like
you get your
super
second
tired
dose or
now.
your first dose?
I got my first dose. Yeah. It was
Which
Pfizer.
one? Pfizer? Okay, I got my
Yeah.
second dose of Moderna on Saturday, and the first dose I was like good. Like I had some arm soreness, but like otherwise I was like chill. Second dose of Moderna, and I've heard Moderna's worse. Which I got Saturday. I was like, I had like a fever, like a really high fever throughout the night. Like I woke up like in a fever. I was like, I got it like 9:30, and then I went through my day, and then I was like getting sick. You know, when you're like getting sick, and you're like, I'm getting sick, I'm getting sick, and then I felt
Yeah.
it, and then I went to bed, and I was like, I'll go to bed. And I usually go to bed around 11, so I went to bed at like 11. Woke up at 2 a.m. and I was like, oh, hopefully I'll sleep it off. Woke up at 2 a.m. full on fever dream. I was like, I was convinced I was in like a Korean spa. I was like, this half of my body's in a Korean spa. This half isn't. I was just very confused about what I was. And then finally, like 2 hours, like an hour later, I got up. I went to the 7-Eleven across my house, got some Gatorade, and was like, and then I was really tired the next day. But now I'm good. I'm good. Now I'm fully vaccinated. So
That's good.
get your vaccines, everyone. Feel free to read. If you want some fun stats knowledge, you can read the paper that CDC released about it. You'll feel really smart and you can explain to people things. You can figure out what the efficacy, 95% efficacy actually means because it's actually a very specific statistic. Anyway, sorry. I am going to sit here and promote vaccines, okay? Come at me, UCLA. Anyway, so as I was talking about, so I had a good day. I went on a walk, walked up to campus. Anyway, does anyone have any questions you'd like me to go over? Mayhaps from the homework that you would like me to discuss? Hold on, I gotta fix it. Okay. So I'll give you a couple minutes to, if you have any questions, to either say them or you can just put them in the chat if you'd like.
I actually had a question about I think it's 3.13.
Okay.
Um I was just wondering like um so for like B and also A, um there's
Sorry, I'm gonna
there's
bring
a
it up.
matrix.
Can you give me one
Okay.
second?
Yeah.
I just
No
thought I wait,
worries.
hold on. I try to unshare my screen when I bring up something. When I bring up, I
Mhm.
like not to show my my Chrome thing on here. I'm always worried something will happen. I don't know what I'm worried about, but okay, let me bring it up and so I can look at it. Okay.
So for like A number 2, like it has like the matrix like H, and also like for B it has the matrix A. Like what like are those like matrices or like Oh wait, I just realized H refers to XA. Never mind. Forget about
Yes.
that. Oh wait, okay. Wait, I'm like, never mind.
Yeah, so
I
A
know what they
is,
refer to now.
yes. Okay, okay, awesome. Okay.
Sorry.
No problem. Does anyone have any other questions you'd like me to go over?
Oh wait, sorry. Okay, I know what I
Go
was
for it.
confused about on that question.
Okay.
It's actually I. Like I don't know what I is. Is that like an identity matrix or is it
Yeah,
just like a
yeah.
random
I is the
matrix?
identity matrix. So I would be
Okay.
the corresponding identity matrix that works. If you ever see
Okay, cool.
I in anything, it's always cool. Okay. If not, let's do a couple problems for fun practice. Okay. So again, if you want me to go over any of the homework problems, feel free to ask, but if not, let's go over some problems. So let's say we have a matrix A, which is this. Okay. So we want to find a orthogonal basis for the image of A. We want to find the kernel of A. I should say a basis. We don't have to do orthogonal. I'll call it orthonormal, actually. Let's do orthonormal. And we also want to find let's do those two. Okay. So how do I find the basis? Well, let's start with the basis for the image of A. Oh no. So again, this might be kind of a review, but it's always helpful. How would I find, what would be the first step in finding the orthogonal, or sorry, a basis for the image of A? Yeah, wait, row reduce, is that what it stands for? REF, row reduce
Yeah,
something?
row reduced echelon.
Oh, I've never seen that acronym. I had a student when I was tutoring individually with people who I did like I tutored for intro linear algebra for like legitimately like 8 quarters in undergrad. Like I was like a student tutor for it. So I've had to teach row reducing about 15 times at this, more than that, like 30, 100 times. So and she used to go through and she'd make me sit there. And you know, when you get into like a basic linear algebra class, like the second half, like it always does like row reduce and then do something. And you know, you try to move on from having to row reduce like step by step. But she would sit there and do it step by step every time. And then she's just like make me watch her. Be like, can you watch me make sure I'm doing it right? I was like, sure. So that was what I did for an hour and I got paid for it. Okay, so I row reduce this because I'm not going to make you row reduce it, and you get this. Okay. So what would be a basis for image of A? Be the span of the first two columns, which would just be 1, 3 and 4, 7. Actually, it also could be just this, or it could also just be, would it? Yeah, right? Because if you have a two-dimensional, isn't any two-dimensional, is it? Actually, I don't know. Is any two-dimensional subspace within R2 a equal to R2. That sounds right. You can't have anything smaller.
I thought last time we said that even if it reduces really nice, you have to just do the original vectors. Like it could be wrong, but I think that's what we said last time.
I can't remember because yeah, we'll just use this. It doesn't really matter. This is not a linear algebra course, luckily. So anyway, so you can use this. And then to find an orthonormal basis, what do you have to do?
Wait, do you have to make it an orthonormal basis in this situation?
You don't have to, but if you want to. One of the questions you have to in the homework. It's not technically necessary. To do an orthonormal basis, you just have to do the Gram-Schmidt process. So it's not necessary. Typically, you want an orthonormal basis because, well, specifically for a spectral decomposition, you need an orthonormal basis. So when you're doing the spectral decomposition of a matrix, right, you need the eigenvectors that you pick to form an orthonormal basis, or else it won't be a spectral decomposition. So to do that, you just do the Gram-Schmidt process, which basically means you go through and you say, okay, if you have like U1 through UN, so V1 is going to be just U1, so it's going to be just 1, 3. And then V2 is going to be, and there's just formulas. It's going to be U2 minus U2 dotted with V1 over V1 dotted with V1 times V1, which would be 4, 7 minus 25 over
Don't you
4.
have to normalize V1?
Yeah, you did at the end, or you can do it now. You can either go through and normalize it as you go, or you can do it. So this will actually produce an orthogonal basis, and then to normalize, you just divide by the length of everything. So it's either way. Some people do it at the end. Sometimes things will do it from this, and then you just normalize both of these. So this would become 1 over 2, 3 over 2, and then you just calculate this out and go through that. So that is how you find an orthonormal basis. Again, something you should be able to do relatively quickly. All this stuff this first week or so, or this first couple of weeks, are all review of linear algebra, but it's always helpful to know what you're doing. Okay, now to find the kernel of A. Again, you just go through and you would say, okay, well, we can just look at the row reduced version and say, okay, we have x1 minus 2x3 is equal to 0, x2 plus x3 is equal to 0. And this leads to basically having x1 is equal to 2x3, x2 is equal to negative x3, x3 is equal to x3. And then you get the kernel of A is equal to the span of 2, negative 1, 1. So all this shouldn't be too difficult. Or the basis of the kernel would just be this. The basis of the kernel. Okay. I wanted to talk about the second question on the homework. Did you guys already all do that question, or have you not done it yet?
I haven't done it yet.
You haven't done it yet?
I've been like too lazy to tackle taking the determinant.
Okay, let me tell you something about it. So if you already did it, I have not. Okay, so let me tell you some things about it. So let me look at it. Let's look at it. So I'm not going to do it for you, obviously, but I just want to point out something. So okay, the problem is to find basically the spectral decomposition, which is the eigenvalue. So spectral decomposition, remember, is A is equal to this U capital lambda U transpose, or is it? Yes, that way. Okay. where these are the eigenvectors. And then these are, this is an orthonormal basis for the eigenspace. So I'll just say orthonormal eigenvectors. And then these are the eigenvalues. So obviously the first, this is basically just a more complicated way of saying finding the eigenvalues and eigenvectors. Okay. So the matrix they give you looks like this. Now I'm going to save you a lot of time here because I want to point something out. Okay. You do not have to find the determinant of this whole matrix. Tayo, do you know what you have to do? Did you solve this and did you go through the whole determinant or did you do something quicker?
I haven't actually done this problem yet, but could you do like
Okay.
a block thingy with a square?
Yes, exactly. Genius. So you do not have to find, so let me just kind of prove this to you. So imagine I want to find an eigenvector, right? So imagine I have x1, x2, x3, and x4. Okay. And then this needs to equal lambda x1, x2, x3, x4, right? So that's the definition of an eigenvector and an eigenvalue. Okay. Observe that this produces the equations of basically you have this times this, right? Because this is going to go out here and it's only going to react with this area, right? So essentially it reduces down to 1, 1, 1, 1, x1, x2 is equals to lambda x1, x2. Okay, and then same with the bottom one here. So x1, x2 never interact with any of this. And then same with the bottom one over here where you get 1 lambda lambda 1 x3 x4 is equal to lambda, sorry, equal to lambda x3 x4. Okay, so you do not have to solve this for the eigenvectors, for the eigenvalues for the entire matrix. Just do these block matrices, and then same thing with the eigenvectors. Okay, you just add on. So solve basically for this, for like each of these, and then for this vector, just add on zeros. Does that make sense? So once you get like an eigenvector for this 2x2 matrix, to get an eigenvector for the whole matrix, just add on 2 zeros above it, and then for this one, just add on 2 zeros below it. Does that make sense to everyone? Or does anyone have any questions about that?
Yeah,
that makes sense. Okay, cool. So don't bother finding the determinant of this whole matrix. You do not need to do that. Just solve for each individual block. Okay. Okay. So then let's go through. So this problem asks you to find basically the eigenvalues and then to find this vector decomposition, right? So part of that is finding the eigenvalues. Okay. And then we're gonna do something with the eigenvalues. So I'm just gonna remind you because sometimes eigenvalues properties are a little bit tricky to remember. So let's look at, does anyone want me to go over how to find eigenvalues or eigenvectors? Do you guys all feel confident finding those? Like just a regular matrix?
Yeah.
You're good. Okay. I don't want to like, I don't want to like do something boring. If you want me to go over it, let me know. But if not, it's okay. So let's look at a matrix with this alpha thing and see what we can talk about with it. So I'm not going to use this matrix exactly, obviously, because I don't want to give the exact answer, but let's say you have this matrix. Okay. So you have this matrix. I think this is what I'm going to go with. So let's find the eigenvector and the eigenvalue. So remember, it's pretty much the same thing over. So let's find the eigenvector. Let me make this alpha. Should I? Yeah, I'll make this alpha. We'll see what happens. Okay, let's find the eigenvalues and eigenvectors. Okay. So to do that, again, I'm going to go a little bit quickly. So you just subtract off lambda. Some people do where you do lambda minus. I've never done that. I think it's sloppy. I'm not going to sit here and lie. And then you just take the determinant. And so it's going to be -6 minus lambda, 5 minus lambda minus, and then this, which is going to be 4 alpha squared. So then just rearranging stuff, we get -30 minus 5 lambda plus 6 lambda plus alpha squared minus 4 alpha squared. Sorry, plus lambda squared minus 4 alpha squared. So then just turning this to a kind of expression, you get alpha squared plus, sorry, lambda squared plus lambda. And then I'll do plus negative 30 minus 4 alpha squared. Okay. And we want this to equal 0, right? So we're just going to have to do the quadratic equation. So that means that lambda is going to equal to, why am I forgetting? Is it, what's the first term? B, wait.
Opposite of B?
Negative b plus or minus, sorry, square root of b squared minus 4ac over 2a. Okay, sorry. That's right? Yeah, okay. So negative 1 plus or minus the square root of b squared is going to be just 1 still, minus 4 times a, which is 1, and then times c, which is this, and then over 2. So then this equals to negative 1/2 plus or minus the square root of 1 minus 120 or sorry, plus 120, and then plus 4 alpha squared over 2, which is going to equal negative 1/2 plus or minus the square root of 121 plus 4 alpha squared over 2. Now, tantalizingly enough, this is not anything of a square, so it pretty much can't be simplified. Just as when you do the homework problem, it ends up a lot simpler than this, just FYI. Like it ends up much nicer. I just kind of put in some random numbers. That's why it didn't turn out very well. But that is okay. So these are eigenvectors. These are eigenvalues, sorry. Now I didn't go through the process of solving for the eigenvectors, but we can do, we can do that, but you would just replace, obviously it's not going to work really for this problem, but you would just end up replacing this and this with lambda and then solving for the kernel, right? So it's not that complicated of a process. And then remember for you want to take the you need to find, so remember for you need the orthonormal basis. So you can't just take the kernel and just leave it there. You need to take to get it and then orthogonalize it. Orthogonalize that stuff. Okay, but here's a question. Okay, question. For what values of alpha is a rank 1 matrix? And what values of alpha is a rank 2 matrix? Now, you can most likely figure this out much easier looking at the matrix, but we're not going to do that. Okay, we're going to be using the eigenvalues. Okay. Maybe take a minute to think about that. Because once you know how to do it, it's a really more of an arithmetic problem. But does anyone know when A will be a rank? What has to be true about the eigenvalues for A to be a rank 1 matrix, and what has to be true for it to be a rank 2 matrix? Does anyone know? Okay, well then, might be a helpful problem to go over. So does anyone know what the relationship between eigenvectors and rank is? So eigenvalues and rank, how are they related? Okay. Well, I'm gonna save you a little bit of trouble. So so the number of non-zero eigenvalues is equal to the rank of the matrix. Cool. So are there values for which we could have a rank 1 or a rank 2 matrix for alpha? Yeah, right. We can kind of adjust it. So if A is going to be a rank 2 matrix, we need the eigenvalues to all not be 0. And if it's going to be rank 1, we need one of the eigenvalues to be 0. So since we have this squared version here, so basically we need to say, okay, when do we have 0 eigenvalue? So obviously that would, what's up? Did someone say something? Or am I just hallucinating? So that would mean that obviously this would have to be 1 because this is going to be a positive number. If we're assuming alpha is a real number, this has to be a positive number up here. So because this is a sum of 2 positive terms. So we just basically have to prove, okay, so when is square root of 121 plus 4 alpha squared over 2 equal to 1/2, right? Because then this would be 0. So if we do -1 plus 1/2, because right, the negative doesn't really matter. We can never subtract a positive number and get a 0. So it's going to be when is this equal to 1/2? And if you solve this, really it means when is 121 plus 4 alpha squared equal to 1, which would be 4 alpha squared needs to equal 1 over 121. Alpha squared. Nope, that is not right. That would be that 121 plus 4 alpha squared needs to equal 1. 4 alpha squared needs to equal 120. Alpha squared equals 30. So alpha can be equal to plus or minus square root 30. So the answer for this would be when.
In this case, wouldn't it be -120? And then it would just not work.
You're so correct. Well, no, it would be thank you. It would be plus or minus root 30i. I guess you can make it a constant. You can make it an imaginary number if you want. A squared term is, well, yeah, that makes sense. Yeah, so it didn't work out perfect, but it works out still. Thank you for pointing out though. Yeah, so it'd still be this though. That would be the answer. It still technically works. A square root always has to be positive, so it still works out. Yeah. Can you have a negative square root? No, you can't. Can you? I don't know. I think it's fine. I think this would be the correct answer. Me not knowing how to do complex analysis. Embarrassing. Cool. So that's how you do that one. The other one you have to do is figure out when is a matrix positive semi-definite. And so remember for that one, just the eigenvalues need to be greater than 1, greater than 0. So you would just, again, solve for when -1/2 plus or minus square root of 121 plus 4 alpha squared over 2 is greater than or equal to 0. It's positive semi-definite. I don't really feel like doing the algebra because it's too complicated, but you can go through and solve for alpha. Solve for limits of alpha. And the homework is a little easier because I believe you have it, like it's gonna work out a little bit easier in the homework for number 2, just FYI. So you don't have to, it won't really be like this, it'll actually be much quicker. Cool. That is problem 2, pretty much from the homework. The next thing is just to think about doing when you have transformations of variables. So basically they say, okay, let's say you have that, you have Z1, Z2, and Z3. And we have that they are distributed with, they have a mean equal to 1, 2, 3. And a variance of this. And then they'll ask you to do something like, okay, let's pretend that y1 is equal to z1 plus 2z3. y2 is equal to z1 plus c2 minus c3. y3 is equal to 2z1 plus z2 plus c3 plus 7. And they'll ask you to find mean and variance of y1, y2, y3. Again, this is all you need to do is rewrite. So the thing that happens is you could go through the whole process of like, there is like a way to do this with like normal distribution of like going through this whole process, but it's very tedious. So what you can do instead is use the properties of mean and variance, and instead rewrite this as a matrix times Z1, Z2, and Z3 because we have properties about matrices multiplied by vectors. So you can just write this as, and just replace all these things with basically like 1, 0, 2, 1, 1, negative 1, 2, 1, 1 times Z1, Z2, Z3 plus 0, 0, 7. And then from there, you can find the expected value of it very easily because the expected value of this based off of linearity expectations just becomes, you can just pull out the matrix. Value of Z1, Z2, Z3 plus 0, 0, 7. And so this would just be 1, 0, 2, 1, 1, negative 1, 2, 1, 1, 1, 2, 3 plus 0, 0, 7. And then you can multiply this out. I'm not going to do that, but. And then similarly with variance, it's pretty similar. So the variance of this, so you can just pull out the constant, obviously, because it's a variance thing. So you can just ignore any added values. And remember, this is just going to be and then the variance B, which I wrote above, and then the transpose. And then you multiply it all out and get the answer. You can also something along the lines of saying, okay, what about like 1/5 times Z1 plus C2 plus C3, like plus 6. And if you'll notice, this is actually 1/5, 1/5, 1/5, Z1, Z2, Z3. They kind of trick you to like make it look different, but it's actually the same. Plus 6, because this is actually a constant. And then you can go through the same process because this is just now a matrix times this vector. And so it's actually the exact same thing. It just looks a little different because you don't have like this is like one thing now. It's really only one line. So you say like y is equal to this. So now you just have like y is equal to 1/5 z1 plus 1/5 z2 plus 1/5 z3 plus 6. And that is how to do the next question on the homework. And then the last question on the homework is just about matrices, and you just multiply them out. Pro tip, a lot of things should cancel out very quickly. And also you should note about how to see if matrices are transposed or not, or are symmetric or not, because you might find that several of them are pretty obviously transposes. And so a lot of the questions ask you to find something and find like the transpose of it. But if it's a symmetric matrix, don't waste your time. Just be like, oh, it's symmetric. It's the same thing. You know what I mean? It will save you a lot of matrix algebra.
Is that for 313 or 313? Yeah.
313, yeah. Oh no, what do you? Oh yeah. So 313, yeah. For example, for B, a lot of them, if you'll notice, are just transposes. So try to take the transpose and see if it's the same as the other thing, because it might be close. Or yeah, or just look at some transposes. I would just recommend, and see what matrices are symmetric. It will probably save you some time. Cool. Oh, that is pretty much how to do all the homework. Does anyone have any questions? How is the class going? How was the meanie? Is this you guys' first time with the meanie, my boy? Let me start.